Name is Cam Himes, and I'm going to be talking about wavelet trees. For an agenda, I'd like to cover wavelet tree construction, just the general algorithm. I'll go over an example for that. Talk about rank and select query algorithms, how those work as we can traverse a tree to find this information. I'll talk a bit about a couple of methods for wavelet tree compression to take better advantage of some of its properties to reduce the space needed. And then I'll cover a couple of interesting applications to solve problems. So as an example, we can consider a string S, which is Mississippi, one we've considered a lot in this course. You can see that Mississippi is made up of 4 characters, M, I, S, and P. So we have an alphabet sigma of length 4. So step by step, what we're first going to do is take that alphabet and partition it into 2 separate parts. Here I'm using 2 equivalently sized parts. They're both of length 2. So the first one, which I've color coded with blue, it has I and M, and the second one has S and P. Now we're going to represent the string as 2 subsequences composed of these separate alphabet subsets. So all you can see here is really the color coding, but you can see that anywhere there was an I or an M in the original string, I've color coded it blue. So those first 2 characters, M, I, are blue. And then anywhere there's an S or a P, I've color coded it red. So it's MI in blue, SS in red, and then I, and then SS, and so on and so forth. Next, we're going to represent the string with a binary encoding. So we're going to take that string and turn it into a bit vector where any characters in the first partition, IM, become 0, and any characters in the second partition, SP, become 1. And again, I'm using the color coding here for clarity, but you can see that all of the M's and the I's became 0s, and all of the S's and the P's became 1s. So the string, which started as Mississippi, now becomes 0, 0, 1, 1, 0, 1, 1, 0, 1, 1. Next, and I just have the same information up top for clarity, we can separate the 2 subsequences based on their membership in the partitions to create our first split that is going to define our wavelet tree. So I basically just took out these characters to create 2 separate subsequences of the original string. We have M, I, and SSSSPP. And now what we're going to do is we're going to repeat steps 1 to 4 for that M, I string and the SSSSPP string until the size of the alphabet we're working with becomes 1, at which point we will be left with a single character in each of the alphabets, and that single character will become a leaf of the tree. Now for visualization, I've got this example pulled up. So as you can see, we have the initial value Mississippi and the initial split IMSP. So we took that string, we created a binary encoding, and then we performed our first split. You can see that the left edge is labeled with a 0. This is just convention, and the right is labeled with a 1. So on the left, we have a new subtree, and this node that starts this new subtree just has the characters from that first partition, so M's and I's, M, I. And now you can see we repeated that step. So we have in this substring the characters I and M, and now we've taken that and partitioned it once more to create 2 more alphabets, each of length 1, and another binary encoding where the M is represented by 1 and the I's are represented by 0s. So we do one more split and we're left with leaf nodes that are just labeled the same as the individual character in the alphabet that we created, alphabets. So we have the leaf nodes I and M. And on the other side with the S's and the P's, we've done the very same thing. We've taken it, that alphabet of S and P, and split it into 2 separate alphabets, S and P. We created a binary encoding and split it, so we're left with the leaf nodes. And at this point, we're done. But it begs a question as to what information is really stored, because I've added some additional information here for the sake of clarity, but we don't really need all this in the wavelet tree representation. So what we're going to end up with is in fact something like this, where we're just storing the bit vectors at each level, and then we have the values of the edges, but we are not explicitly storing the original string. So we're not storing Mississippi, we're not storing MMI. We don't have something explicitly denoting the split. It's just clear where it splits. So let's talk about rank queries. If you recall, rank IC is a function that returns the number of occurrences of the character C up to the ith position in the text. For the sake of wavelet trees, we'll be using a slightly modified version to support a recursive approach. And I have seen another approach, which is iterative. It just uses a while loop, but I believe this is the most efficient. So here we have a function which looks a little bit different. The notation is a bit different. So it's rank underscore C. It's still really a parameter of the function, but this is the character we're looking for. We pass in BWT. I'll explain in a second, as well as I, L, and R. So I is the same as it was before, the ith position we're looking for, same with C. BWT is the Burrows-Wheeler transform of the original string. So this is a transform version of the string we're familiar with, where similar characters are clustered. This isn't used in the example I provided. We're just using plain text Mississippi, but oftentimes for a wavelet tree, we'll be using the Burrows-Wheeler transform and passing the same one in to every function call. And then L.R is a range of indices within the wavelet tree where the search is currently focused. And this isn't actually a substring of the original string, so these aren't indices to narrow down our focus in Mississippi exactly. It's just that wavelet trees represent these hierarchical partitions of the alphabet. So at each level, as we go with rank, and you'll see as we go with select, we're going to be focusing on only a subset of the characters. So the range, these indices, are limiting the search to specific nodes at each level within the alphabet. So we're progressively narrowing down as we recurse, as we make more function calls. Essentially, L and R describe what portion of the alphabet we're considering at a given point. Now, put formally, we have this function. It says if L is equal to R, so basically if we're only looking at one character, right? Because as I said, L and R describe a subset of the entire alphabet. So if L is equal to R, we are looking at only one character, then return I. Otherwise, we're going to be doing this recursive process where we calculate a middle position. So it's like in the middle of L and R. This is us splitting the alphabet. Now, if this character, which we're looking for the rank of, is less than or equal to the character at the middle point that we've just calculated of the alphabet, then what we're going to do is essentially we're going to move down into the left node. And what that looks like is we are going to be considering the same BWT, the same character, but in this function call you can see we pass in the rank of 0 because by convention the left child is connected to its parent with an edge which is labeled 0. And we're going to be passing into that B, L, R, I, and then L up to M. So it's like we're considering the left portion of the string. And this will all make more sense when I can work through it with an example so we can see sort of what I'm talking about. But the else condition, if C is basically greater than that middle character, what we are going to do instead is consider the right child. So importantly, you can see that we're looking for the rank of 1 because 1 is the convention denoting this right child. And then instead of looking from L to M in the alphabet, we are looking from M plus 1 to R, so the right portion after that alphabet. So let's take a look at an example. This is using a Burrows-Wheeler transform. I'm not sure what the original string is, but this is from the textbook. So you can see we've got a string here, which is made up of T, C, A, and $, which is, a characteristic of a Burrows-Wheeler transform string. We perform a split. So on the left side, you can see the A's and the $signs go there, and on the right side, C and T. And as the textbook described it, it's convention, and in fact, I think necessary for preserving runtime for some algorithms, which I think we'll see later, to basically perform these splits in lexicographic order. So sort the alphabet first and then perform your splits. So that's why you can see $, which they're considering at the start of the alphabet, I believe, comes before A. And so what you'll find now looking at this tree structure is that if you read the leaf nodes, the labels on the leaf nodes from left to right, it's sorted. So $, becomes first, and then A, and then C, and then T. But okay, pretty standard. It looks a lot like our Mississippi tree. So in this recursive approach, suppose we're looking for the rank of this character A in this Burrows-Wheeler transform string up to 7. So we want to understand how many times does A happen up to the 7th position between 1 and 4. And I'm passing in 1 and 4 as the initial here. Really, 4 can just be the size of the alphabet, lowercase sigma, because we are initially considering the entire alphabet. We haven't made any recursive calls at this point. So we can zoom in here and just consider the root node for a second. So A is in the left partition the same partition as the dollar sign is $A. So it'll be represented by a 0. We know it's going to that left child. So what we can do is we can look for the rank of 0. And here I did pass in lowercase sigma, the rank of 0 up till 7, 1 sigma. And we find that that's 3. So up to the 7th position, there are 3 zeros in this bit vector which we're looking at. However, these zeros we know because the alphabet subset is $A, these zeros can either represent an A or a dollar sign. And keep in mind, in the actual wavelet tree, we don't have access to the original string because that takes extra space. So we can't be sure whether those are A's or dollar signs. And that's why, okay, we find this is 3. We find there are 3 zeros. So we know kind of that the answer is at most 3. If all of those were A's, it would be 3. But now we can move on. We go to the left because it's in the left subchild. And here we find that A is in the right partition. So it's going to be represented by a 1. Now we change the function call a little bit. So instead of looking for a 0, we're looking for a 1 because A used to be represented by 0. Now it's represented by 1. We are looking for the rank of 1 up to position 3. And we are considering it in the indices L and R 1 and 2. So why 1 and 2? Because $ and A are the first 2 characters in the overall alphabet. So this is kind of just a way of describing what node we're looking at the moment. This node is representative of this subset of the alphabet from index 1 to 2. And we pass in 3 here. We're kind of taking care of the offset here. So we're looking for how many 1s happen before position 3. So we find that this is equal to 2. And now we can move to the right. We know that A is in the right. And we found that we've encountered a leaf node, which indicates our previous answer 2 is the final answer. And I want to be clear here when I say accounting for the offset, right? It's like I said before, when we did this initial step, we found that there were 3 zeros, but they could be A's or dollar signs. So when we move on, we're looking at these characters here. We know that the first 3 zeros, which are either A's or dollar signs, happened before position 7, and then they got transferred down here to the left child. And now, those first 3 zeros, we want to know how many of those were A's. That's essentially the question that we're answering with this rank query. So we look and we see that there are 2 1s in the first 3 positions, which tells us that of those 3 zeros which occurred before position 7, 2 of them were A's, which is what makes our final answer 2. And this could keep going, and essentially at each step we're narrowing down, trying to understand, what portion of these zeros are actually representative of A's versus some other character. Now, select queries. And I'll talk about runtime for these in a little bit. Select queries. Recall that select IC is the position of the ith occurrence of the character C in the text. So a bit different than rank. Now, suppose we have this same tree, which we're familiar with now, and we're trying to find select for the character T over this BWT. So BWT is a parameter here too, but it's not changing in between function calls. So kind of goes without saying. We're seeing what is the position of the second occurrence of the character T in the string. So let's see how we go about this. Instead of starting at the root node, we're actually going to be starting at the very bottom, and specifically starting at the leaf node representing this character T. And you'll notice as I go through these animations that I'm omitting parts of the tree. They didn't go anywhere. It's just they're irrelevant to solving this problem. So our focus here lies with the leaf node representing T. And what we're going to do is move up to its parent, and there's only one choice for parent. Each node has one parent. And we are going to run a select query. So we know that T is represented by 1 here, so we're looking for 1s. And we want to know how many of these 1s occur within the first 2. So these 4 characters here, the 1 0 1 0, these will tell us the positions of all the T's potentially. We just have to take care of what some people might refer to as an offset. And what I mean by that is that the 1 0 1 0 we see here, the bit vector at this level of the tree, doesn't necessarily represent the positions in the original string. You can imagine that at our first partition, and I'll go back here, I mean, you don't even have to imagine, you see these first 3 0 characters in the original bit vector at the root. these went to the left tree. So it's like the positions aren't maintained at each level of the tree. We have to account for the fact that it's shifting, that some characters are going to the left side, some to the right side. So we run the select query, and so we can see the position of the second occurrence of a 1, because if you think about it, that's the second occurrence of t. And what we find here is that it occurs at position 3, 1, 0, 1. So the second occurrence happens at position 3. But that might not correspond to position 3 in the original string. And I think I'd said that the BWT wouldn't change between function calls. I guess to be clear, it will change in that we are only looking at a specific substring or subsequence, rather, within the original of the original string. So here we're looking from characters 3 to 4 within the alphabet. Again, a slice of the alphabet, not a slice of the original string. So now we move up to the parent again, having that result of 3, and we look for the position 1 over the entire string from 1 to 4. There are 4 characters in the alphabet. We are running a select query again on 1 because TCTC, both of these characters are represented by 1, of 3. So what is the third position of a 1? Because we already know from that previous select query that the third position, or rather that the second position of t corresponds to the third position of a 1, and here we find that it's 6. And kind of like with rank, once we reach the root, this is the inverse, but once we reach the root, we know this is our final answer. So we found that the second occurrence of t happens at position 6. Now, in terms of runtime complexity, I first want to note that the tree height is assumed to be the ceiling of log base 2 of sigma, lowercase sigma, the size of the alphabet, assuming a balanced wavelet tree with even alphabet splits. So as you go down the tree, there will ultimately be sigma leaf nodes, and so the height of the tree is going to be log base 2 of sigma, because at each position you're kind of having it. So for rank, we're traversing the tree from the root node to a leaf node. And at each level of traversal, we use pre-computed rank support structures, which I didn't really mention, but on the bit vector to compute rank in O of 1 time. And I'll talk about those a little bit in a second, but this is just referred to as Jacobson's method. He's the one who discovered it. So therefore, we're performing a constant time in O of 1 operation log base 2 of sigma times, because that's the height of the tree. So the worst case runtime is simply big O of log sigma. Very similarly for select, we are traversing the tree, this time from a leaf up to the roof node, and at each level of traversal, we use pre-computed select support structures on the bit vector to compute select in constant time. I said this is Jacobson's method. I believe this is actually Clark's method. Therefore, we're performing a constant time operation, very similarly, log base 2 of sigma times, so the worst case runtime is the same, big O of log of sigma. Now, in terms of the space complexity, the overall here is n times the ceiling of log sigma plus little o of n log sigma bits. So the first term here, the bigger one, n log sigma, represents n times the ceiling of log sigma, represents the space needed to actually store the bit vectors. So there are log sigma levels in a balanced wavelet tree, which we discussed. Now for each level, we have 1 bit for each character in the input string stored as separate bit vectors. And what I mean by that is if our original bit vector, our original encoding of the string is 11 characters, which would correspond to a string of 11 characters because each one becomes 0 or 1, then as we go down the tree, we are going to have these characters split up into separate bit vectors, but they're all going to sum to 11 each time, all the way down to the very last level before the leaf nodes. So the total space across all levels to store these bit vectors is n times the height of the tree log sigma bits. The second term, O little o of n log sigma, represents additional but sublinear space needed to support these constant time rank and select operations on the bit vectors. Each of these structures is a dictionary, essentially, of size O little o of n bits for each bit vector. So since we have the ceiling of log sigma levels, the cumulative space that is needed for those support structures is a little o of n times log sigma for an overall space complexity of O in log sigma. Now, the support structures I'll mention briefly, not really in detail, but they're very similar. The rank support structure is a sampled hash map, which I believe we've discussed in class, which stores pre-computed counts of the rank, the zeros and ones up to each position in a bit vector. The keys for this dictionary hash map are the interval positions, and the values are the cumulative counts of zeros or ones. So basically, when you want to access something, you can pass in a position, and if it exists in the hash map, then you can immediately grab it. If not, you can make some very small number of steps, depending on how frequent the sampling is, in order to, in constant time, get the value you're looking for. So this enables constant time rank queries and uses little o of n bits per bit vector. Very similarly, select is stored in a hash map where we have keys for internal counts. Also using sampling here, and the values are positions, so this enables constant time select queries. In terms of wavelet tree compression, there are two ideas I'm going to mention here. I know there are more, but the first is entropy coding, and the second is actually changing the tree shape. So for entropy coding, I would suggest looking at a string like AAB, AA, $BACA. So looking at this, clearly the character A is dominant. It appears more frequently than B, C, or the $. And this difference in character frequency, just generally speaking, indicates the potential for compressing the bit vectors. So the basic idea is to compress the bit vectors in the wavelet tree using a zero-order entropy coding method like run length encoding. So zero-order entropy compression sort of explains the minimum number of bits needed to encode a sequence based on the frequency of the symbols. In our case, we have bit vectors, so we're just thinking about zeros and ones. So we can use run length encoding to take a vector which looks like 11110000 and store it as 1404, meaning there are 4 ones followed by 4 zeros. After compression, I think we'd have to adjust the rank and select support structures a bit to ensure efficient operations across these compressed bit vectors, but we could still allow for constant time queries. And with this method, we can achieve a space complexity of n h sub 0 of s bits, where h sub 0 of s is a function computing the empirical zero-order entropy of a sequence S. Another method is just changing the tree shape. So far, we've kind of ran with the assumption that the tree shape would be balanced, but the basic idea here is to use a Huffman-shaped wavelet tree instead of a balanced one to reduce the storage space and to improve the average query time, depending on how you're querying. So a Huffman-shaped tree is simply a tree where each node has either 0 or 2 children. And in a Huffman tree, the more common a leaf node is, the closer to the root it is. So less depth. Now, if you recall our first example, we used a balanced tree for Mississippi. So we had a split at the very root of the tree IM and then an SP. So it split into 2 and then split into 2 again. All the leaf nodes are at the same level. But with a Huffman tree, we can make an observation about this and say, well, if we look at the frequency of the characters in the string Mississippi, it looks like there are 4 occurrences of the character I, 4 occurrences of S, 2 of P, and 1 of M. So we can reorganize our tree to create a Huffman-shaped version. And you'll notice the splits are quite different in this one. So instead of splitting evenly at the root, instead we are going to immediately split left into I and then right into M, S, and P. So if you go left of the root node, you immediately come to a leaf node, which is labeled with I. If you go to the right, you have a bit vector representing the subsequence made up of all characters which are not I, so M, S, 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 P, P. If you recall, S is really tied with I for frequency because it occurs 4 times, same with I. So now we'll split off S, and I think that was kind of an arbitrary decision to split S and I separately like this because they're both the most frequent. But clearly they're more frequent than M and P. We go down to the right again. We have a subsequence MPP represented by 100. And at this point, if we did have to split again, we would choose P first to have its leaf node first because it occurs twice where M occurs only once. But we are only left with 2 characters in the alphabet, so we might as well just split completely and end up with 2 leaf nodes. So You can see now that if we were running rank or select queries on I, for example, you know, with rank, we would start at the root and then go down. With select, we would start at the leaf and then go up. But either way, it's going to happen in one step, whereas with the balanced Mississippi tree, and in fact, I can go back so we can take a look at that, you can see that for either of those operations in I, you would have to traverse log sigma steps, because you'd have to go from I to its parent node and then from its parent node to the root. So in general, this method can achieve space close to that same thing we just discussed with the other compression method, nh sub 0 of s. I might be mispronouncing that. I apologize. And when rank and select queries are run on characters in proportion to their frequency, common characters have reduced average query times compared to balanced wavelet trees. So this is just a way of saying, if you are, for example, looking at for i's and s's more often because they appear more often in the string Mississippi, then you're going to have a better average query time. Because with our Huffman trees, queries for I will be, relatively speaking, fast, as I've just demonstrated. S will actually be the same because it's also at depth 2, as was the case in the original tree. And then you can see for M and for P, they're actually at a depth of 3. It depends how you count it. You can count depth a couple of ways, but it's clearly 1 deeper than it was in the balanced wavelet tree. So for M and P, it'll actually be worse, and that's a limitation, that the worst case access time becomes worse for infrequent characters as they have longer paths. Finally, I'm going to cover a few problems that we can solve using wavelet trees. So the first application is counting occurrences in an interval. Given a string S in interval I to j and a character C, we want to find the number of times that C occurs within this interval S from I to j. The basic idea is to check the rank at the end position and subtract the rank at the starting position -1. Suppose we're looking to see how frequently the character C occurs within the interval 3 to 8 of some string we've created a wavelet tree for. The occurrences of C within that range is equal to rank C of 8 at position 8 minus the rank of C at position 2, 3 minus 1. And ultimately, for our previous example, this evaluates to 1. Now, in terms of runtime, we've previously determined that rank is a O of log sigma operation. So we're traversing down the tree, and since each level of the tree requires a constant time rank operation, and there are log sigma levels, at least in a balanced wavelet tree, the overall runtime is still big O of log sigma. Now we can adapt this to count occurrences within a subset of the alphabet in an interval. So given a lot of the same starting points, a string S, an interval I to j, and a subset of the alphabet A, we want to count the total occurrences of all characters in A within this interval. So for each character in A, we can just defer to the previously described algorithm and sum the results of that algorithm for each character to get the final result. Now, since the previous algorithm runs in log sigma time, and we have to run this algorithm for each character in A, the runtime of the algorithm is simply big O of the size of A, the size of that subset of the alphabet, times log sigma. One final problem is kth smallest element. So for example, if we want to know what is the third lexicographically smallest character that appears in the subarray from index I equals 2 to I equals 8. So working again with this same wavelet tree. First we can look and say, well, from 2 to 8, actually this is the string, and we wouldn't know this based on the wavelet tree, but we know now, it is $ATCA. So first we can count how many elements go to each child in the range from 2 to 8. So this range we're considering. And we can use this previous algorithm we've described. So we take the rank of zeros for this substring $ATCA at 8 and then subtract the rank at 1. So we're finding it in the interval as previously described. And in this case, we find that there are 4 zeros here and there are 3 1s. So since the first 4 smallest elements go to the left child, we're going to move to that node because the third smallest element that we're looking for is going to be in there. And there's sort of an implicit assumption here that the wavelet tree was created with partitions based on the lexicographical order of the alphabet. So if you'll notice looking at the partitions here, as I previously described, this is how the textbook describes the construction of a wavelet tree. The leaf nodes, if you follow a level order traversal, are going to already be in, I keep saying lexicographical, I'll say alphabetical order. So in this case, our partitions are $A, CT, because that is the alphabetical order. And that's how we know that we should move to the left child here. So moving along, we know that in the range 2 to 8, 4 characters went to this left child, so we're going to look in the range 1 to 4 of this left child's bit vector. And in this case, there's no offset needed because the zeros from the first bit vector, the roots bit vector, went to the left child. And if you look before the range 2-8, we have 2 1s. So in this case, it's irrelevant, but it's possible you could use, or you could require an offset in order to get the proper range to look for in this child. So again, we can count how many elements go to each child in the range. We don't have to use 2 rank functions here. We can just use 1 because we're starting from the very start of the subsequence. So we compute the rank of 0, and that is 1, and the rank of 1, that is 3. Now, since only 1 element will go to the left child, we know the third smallest element is in the right child, so we're going to move there. Moving along, we've now reached the leaf node for A, so we know the answer to our query. The third smallest element in this substring, is A. Finally, I want to give a few acknowledgements, resources I've looked at to create this presentation and to learn about wavelet trees. So Ben Langmead is a computational biologist, and he put out a couple of videos about wavelet trees that helped me to understand the basics. And then I may mispronounce some names, but Enno Ohlebusch, he wrote the bioinformatics algorithms textbook, which I also refer to throughout this for algorithms and various information. Gonzalo Navarro is a computer scientist. He wrote a paper called Wavelet Trees for All that had some interesting ideas in general, but specifically I think I got a lot of the compression information from him. And then 4 people, Robinson Castro, Nico, Lehmann, Jorge, Perez, and Bernardo, Subercaseaux, wrote a paper called Wavelet Trees for Competitive Programming, where I pulled some of the applications from. So thank you for listening. I hope this was informative.